Welcome back. We have covered a lot of ground in our discussion on evolution. So we've talked about the history of the people who influenced Darwin and Darwin's own journey in coming up with his theory and Russell Wallace's um, theory at the same time. And then we've talked about different modes of evolution and a little more in depth into how natural selection works. And now we're going to kind of look at all of the evidence, some of which Darwin saw and some of which he didn't, that all supports this theory. So, the pieces of evidence that we're going to be talking about are, first of all, looking at the fossil record, and then biogeography, comparative anatomy and embryology, molecular biology, and lab and field studies that all support this hypothesis that organisms evolve, which is how it becomes a scientific theory, that there's so many pieces of evidence supporting it. So first, we're going to look at the fossil record. And if you recall, Cuvier was the one who realized that fossils were not just dead animals or dead organisms, but organisms that no longer existed, that had gone extinct. Um, and the fact that species can change over time, either the same species can develop adaptations and look physically different, or one species can go extinct and another species could evolve, is evidence of evolution. That in and of itself, that species don't just stay the same all the time, that's evolution. A great animal to look at when we're looking at evolution and changes in the fossil record is the horse. So horses have changed drastically over the past like 50 million years. And we can see, looking at these kind of paintings at the top, the modern horse is on the right. This is the wild horse, the Przewalski horse, which they actually have at the National Zoo. Um, and then moving back in time to the left, all the way to the Eohippus. And if you're looking at that, I want you to just think for a moment of the changes that you see in these pictures. So think to yourself, like, what is changing over time? So take a minute, pause, and think. Okay, hopefully you saw the animal is getting bigger, the head shape is changing, some of the spots on the fur, which are just being guessed at here, right? Obviously, nobody really knows what they looked at, but the fur is changing. The background is changing too, right? The actual environment that this horse is living in has changed. And that is what is driving the change in the horse itself, right? So this Eohippus looks like a small, very like a maybe smaller than a deer. Um, and it is a good size for like hiding among the in the forest, right? This looks like a kind of jungly forest area that it's living in. And the climate and where the fossils were found kind of indicate that this is what it looked like when it lived there. As we move forwards in time and the environment gets drier and more of the grassland like, there are fewer places to hide. So rather than hiding, there's now an organism that would benefit from running and running fast, right? So its entire body has evolved because the individuals who could run faster were the ones that survived, right? It's not that they tried to get taller or faster, but it's just those individuals who had an adaptation that made them faster or made their legs longer were able to survive. They also their head shapes changed and their jaws because the foods they were eating were different, right? So to take advantage of different foods, that was an adaptation. Now, if we look at the bottom here and really focus, if you can kind of zoom your screen in on the leg anatomy that we see here, if you look at the Mesohippus at the bottom, you can see that it's got 3 toes. So I'll kind of draw where those it looks like this, right? And it's walking on all 3. As we go up in time, you can see the Meryhippus or Merychippus. Those side toes are much shorter now. They're not touching the ground anymore. They're just kind of there, right? And obviously, this animal was stable enough um, not to need to run on that. That's kind of like a modern dogs. They have that dew claw that's up there that doesn't really do anything, right? As we go even more recent in time to this pliohippus, you can just barely see little nubbins sticking out there. So those bones have completely fused by the time we get to today's horse, right? All of those bones have fused together. They didn't disappear, but they've shortened and fused. Because this is a more stable and faster way of running for the modern horse. And so any small individuals to maybe get more food, get away from predators, and therefore have more opportunities for breeding and pass those genes on. Darwin predicted, but he didn't live long enough to see, that we would find transitional species like this. He said, you know, if the fossils are the dead things and I'm looking at the live things, we should be able to see like kind of these missing links along the way. And the horse is a great example of that. Another missing link is the Archaeopteryx. And I don't know how many people have seen this before. This is kind of that transitional species between extinct dinosaurs and birds. Birds are actually a dinosaur. They are living dinosaurs, and they were a branch of the dinosaur. And here we can see kind of the evolution into modern birds. So this was found in the 1800s in Germany, and they've since found, I think, about 40 of them. So take a minute and look at what features of this look bird-like, and what features of this fossil look more dinosaur-like. So just pause and examine it for a moment. Okay, so now that you're back, so the dinosaur-like features, one very obvious one is this tail, right? Birds do not have a bony tail. They have feathers coming out of their tail, but if anybody here has ever touched a bird, there's no bone there, right? It's just feather. They also, which is hard to see here, there are some teeth, and it's got some claws on its forelegs, which birds don't have, although there is one species that where the chicks actually do. So these are the dinosaur features. Now the bird-like features here, obviously the head shape, right? This really looks like a bird. And already we've got these long limbs, and they've lost some digits, right? It doesn't have 5 digits like some other vertebrates do, or even 4, right? We just see three here. And the other really obvious bird-like feature are the feathers, right? So this is a feathered animal. It may have been able to glide a bit. The feathers were likely originally used for thermoregulation, just to kind of keep it warm, but then had been co-opted for gliding and eventually became used for flight. So these are some really strong, these transitional species, these missing links are really strong evidence for evolution and change over time. The next piece of evidence that we're going to look at is biogeography. And this means the geography of where things live, right? The biology of the geography. So looking at where things live can give us a really good clue to what they evolved from, right? Things are more closely related to things that live near them. So this is just studying the distribution of what lives where. And things live based on, are distributed from where they had a close relative. And you can look at, a desert in the North America and a desert in Africa, and the species are going to be different, right? They're both adapted to desert living, but it's not like here are the 5 desert species that get plopped in every desert. No, the African desert animals have evolved from other African species, and the North American desert animals have evolved from other North American species. And species on islands are descended from species on the mainland that live near them. So you're going to find a close relative on mainlands, just like Darwin did with the finches on the Galapagos and the finches in South America. So islands themselves often have endemic species, which means they're found nowhere else. There are other places that have endemic species as well that are found only in one location. But often an organism from the mainland will make it to an island and then have different competition, different food resources, different environment that it over time adapts to and becomes a new species in that process, right? It evolves into a new species that is found only there. So some examples are lemurs on Madagascar. Here we have below the lemur is marine iguana in the Galapagos. In the middle here is an iiwi in Hawaii. On the top right is a kiwi in New Zealand. And on the bottom right is a Galapagos tortoise. So all of these are unique species found only there. There are other species of giant tortoise that are not in the Galapagos. There's one other island in the Indian Ocean, the Aldabra tortoise, that's a giant tortoise. And that's actually, if any of you have seen the giant tortoises at the National Zoo, those are Aldabra tortoises. So similar selection pressures acted on them, right? So a turtle went from the mainland to an island, very little competition, lots of food, and they could just grow big. And there were plenty of resources for them. So over time, right, there was selection for larger and larger size. So they ended up looking very similar, but the Galapagos tortoise is, if you do a genetic research, is more closely related to a turtle on the South American mainland, and the Aldabra tortoise is going to be more closely related to something either on the Asian or the African continent. I'm actually not sure. Another really cool piece of biogeographical evidence is looking at ring species. So these are species where small changes have been made over time as a species distributed itself. So much so that by the time it has completed its distribution, it has large changes have built up. So if we look at this species of salamander, at the top we have the original species. This is a salamander. We're looking at the coast of California and Oregon here. So the species started in Oregon and kind of worked its way down. And as it got to the Californian desert, this is the San Joaquin Valley here, it can't live in the desert. And so some of them went west towards the coast, and other ones went east, a little more inland. And as they moved, either just mutations built up, or maybe there was some selection for different coloration, but they started to change how they look. So you can see they're slightly different colors. By the time we get to this one here that I'm circling, it's black and yellow splotched, right? And the ones that kind of moved along the coast are more red and maybe stripy, and then we end up with one. The furthest south is black with red stripes. Now, something about a species that we haven't talked about is that they can interbreed with each other and produce fertile offspring. So that's one definition of a species, is that they're willing to mate with each other, they recognize each other as the same species, their offspring are fertile, so they could mate as well. If we number these guys, 1, 2, 3, 4, 5, and then this will be 2A and 2B. So the ones with A and B are have kind of come down from the other side. 1 can mate with 2, 2 can mate with 3, 3 can mate with 4, and 4 can mate with 5. They're all a species. 1 can also mate with 2A, and 2A can mate with 2B. So they're the same species. But 2B and 5 cannot mate with each other. They're too different. So either they don't recognize each other as the same species, they say you're red where you should be yellow, or when they mate, it's incompatible and they're unable to have offspring, but they are not the same species anymore. So this is showing us that these small changes are building up over time. Another cool piece of biogeographical evidence is looking at the distribution of species today and figuring out kind of how that distribution came to be. So if we look at marsupials, they exist in North America, South America, and mainly Australia, but North and South America have the opossum. The marsupial is very different from other mammals, right? They're born very, very premature. They crawl out of their mother, and then they crawl up and find the pouch and climb into the pouch when they're this tiny, tiny little jelly bean-like embryo. That is very different from placental mammals, which all of us are, right? That develop inside their mother and finish most of their development, as a fetus. So the chances of that evolving twice would be really, really low, extremely low. And so someone hypothesized that, well, they must have had some way, if we have this current distribution of marsupials today, they must have at some point crossed over Antarctica to get to Australia, and when this was all one landmass. And so if we were to look at Antarctica, we should be able to find marsupial fossils. So that was an observation and a hypothesis, and a prediction, right? If that was their distribution, then we should find fossils there. And you actually can find, they have found marsupial fossils in Antarctica. So this is, evidence that they did make that move from North and South America over to um, Australia. Okay. Our next piece of evidence, I think we're going to stop here. This has been a lot of information. So we'll stop here and we'll pick up with the next lecture, with the rest of our evidence.